Thank you for the nice introduction and the invitation. I'm excited to be the first speaker of this day, which focuses on mostly questions around open quantum systems and how we deal with them on a quantum computer. And so this is joint work with Anthony, Michael, and Fernando. Well, this will include some physics notation and concepts that you may not be super familiar with. So please, as in the previous days, don't hesitate to interrupt me and ask questions. Okay. So open quantum systems, what's the story behind? We typically have some small quantum system that we want to understand, but unlike in the future of quantum computers where we hope that we have error-corrected qubits that are completely separated and well described, in nature everything is much more messy. You have lots of interactions between the rest of your universe with the small system that you care about, and so there is some sort of coupling between the small system that you want to understand and the large environment. You want to understand the emergent behavior from such interactions. And early proposals, I mean, people realized in early time that this quantum thermodynamics and these kind of questions are very important for understanding nature, and because it involves quantum effects, probably we don't have much hope to simulate those on a classical computer, but now that we have a well-established model of quantum computers, that was the case in the 90s, people started thinking about simulating such scenarios. And so the earliest paper I know that attempted to answer this question is from 1998 by Barbara Terhal and David DiVincenzo. And while the idea was just to simulate both the system and the environment on the quantum computer, so just simulate all relevant parties, put them inside your quantum computer that you can control and understand well, and then you just forget about the environment part and only study the properties of the subsystem. Now, this should obviously work, because if you can simulate the large system, which now you can treat as a closed system, then we have algorithms, even by then, Hamiltonian simulation and all tools for simulating pure dynamics, coherent dynamics. And this way, you effectively get an incoherent dynamics of the small system. But it's very resource intensive, because I mean, these couplings and these descriptions will be effective once the environment is much, much larger than the system that you care about. So in order to, I don't know, simulate your 50, 60 qubit system, you would need to add lots of ancillary qubits, I don't know, tens of thousands probably, to make this effective description accurate. And well, we don't really want to use 10,000 logical qubits when you have a hope to get away with much fewer. People indeed looked at this question, and there was some development that I will flash a few things about. But the hope is that we can simulate the subsystem that we care about and only effectively describe what's happening to the qubits that are in the subsystem that we really want to study. And so an idea to somehow forget about the environment and not representing them on a quantum computer while you do simulation is that you describe the effective dynamics on your subsystem using what is called the Lindbladian master equation. So this is an effective description of what happens on your subsystem, assuming that your bath is much larger than your system and it basically continuously refreshes. So as time evolves, the tiny interaction coming from your subsystem has negligible effects, and the qubits that maybe were interacting initially with the environment, within the environment, they got shuffled away, and you can basically treat your bath as a constant system. It's continuously refreshed. And under such assumption, you can derive the effective dynamics of your system, and this is called this Lindblad master equation, which holds under these assumptions. And this is an equation that describes the time evolution of your mixed state rho, your density operator. It has two parts. The first part, that's really just the Schrödinger equation expressed in this density operator formalism. So the first thing is the coherent part, but that you already know how to deal with. So in this talk, I will focus mostly on the dissipative part, which is describing these losses and incoherencies that come from interaction with this large bath. And while this has the form that is written there, if you haven't seen it, it can look intimidating, but I will try to shed some light on what these things mean. So these LJs, they are operators of size matching the dimension of the system. And so this overall part is the dissipative part. And when you apply this LJ dagger to rho, imagine that you have a pure state there, then basically you apply this operator LJ to the pure state. And this describes the transition, how your state changes according to these interactions. But to make everything trace preserving, so preserving the overall state, then when you make a transition, you need to account for the decay that previous parts of the state move to new parts. Therefore, this term has to be added. And it turns out that, well, if you have this equation, you can just describe this entire operator as a super operator on this density operator's rho. And this is called the Lindbladian, the overall operator. And these LJs are called the Lindblad operators. So these are individual jump or Lindblad operators. And the entire thing is called the Lindbladian, the super operator. And as I said, these LJs describe these infinitesimal quantum transitions. And well, it's a linear differential equation. So how you solve that? You just exponentiate the operator, which appears in this linear system. That is the Lindbladian. So you exponentiate the super operator, and you get the time evolution for a time t interval. So this is how you can effectively describe the evolution of your system in this open system picture. And the good thing that here, nothing about the environment appears explicitly. These jump operators are implied by the way your subsystem interacts with your environment. So all the effects of the environment are kind of compressed down to these Lindblad operators and this Lindbladian in general. And well, I would like to give some more intuition about how to think about Lindbladians, especially if you are not so familiar with this thing. And let's get back one more step to the classical case, and you have just classical probability distributions, which are classical analogs of density operators, but they are always diagonal, of course. And so there, we also have an analogous dynamics, and that's called continuous time Markov chain. And they also have some generator, L, which is a Laplacian matrix. So the off-diagonal entries of L are now these non-negative jump rates, which tell you that from state I, how likely are you to jump to state J on the unit time, basically, something like that, or infinitesimal time interval. And diagonal entries, you should put the minus of the sum of all the off-diagonal elements. So all the jumps that you are transitioning away from a state means that you decay at that position. And well, if you have a matrix which satisfies this, that all of the diagonal entries are non-negative and the diagonal is the sum of the minus of the off-diagonal entries, then this is called a Laplacian matrix. And well, you can describe it as a weighted graph if you wish, where the weights describe the likelihood of transitions and so on. And similarly to what happened in this quantum case, this gives rise to a linear differential equation, which you solve just by exponentiating these Laplacian matrix. And that will always give you a Markov chain, so a stochastic matrix that describes, if you exponentiate for time t, that like how the jumps look after waiting for time t from the initial state. And the same thing happens in the quantum case, but there you are exponentiating a super operator because you already act on density operators rather than just vectors which are distributions. And there also, if you have a Lindbladian in the form that I described, then always this exponentiated superoperator will be a quantum channel that is a completely positive trace preserving map, which is the quantum analog of Markov chains. Okay, And then here, once again, just this is how the Lindbladian looked like. And please don't confuse the Laplacian L, which was just this matrix of generator matrix in the classical case with Lindblad operators that are also operators, but they transitions to the individual jumps in the quantum picture. And this, of course, this coherent evolution part that has no classical analog, but once again, we will not focus too much on that part in this talk. We rather want to understand how to handle this dissipative part. Okay, please.
Yeah, you mentioned this is a symmetric generator L. Why the graph is directed? If it's symmetric, it's...
Yeah, okay, sorry. That's right. In general, it doesn't have to be symmetric.
Okay. Yeah.
But it's easier to understand that it's symmetric, but okay, yeah. Let's forget about symmetric. In general, it is just a matrix with satisfy this. It's symmetric, there is some additional properties that make it a bit easier to handle. But in general, yeah, you don't.
Sure. But if it's symmetric, then it's undirected, right? I just want to clarify. Because you stated the first line. Is that right?
Yeah,
okay.
Right. Okay, so if it's, yeah.
Okay.
Symmetric, then, yeah, the weighted graph picture is why I wanted to impose the symmetry, because then it's very nice. Otherwise, you would need a weighted directed graph to describe it. Yeah, sorry for that. It was a little bit confusing, but thanks for the question.
Yeah, so so you said in the classical case, if I treat like my probability distribution as a vector, you know, I'm sort of applying the Laplacian. But what if I like embedded my probability distribution, you know, as a diagonal of a density matrix, like a diagonal density matrix? Then what would the Lindblad operators look like for that case?
Oh yeah, that's a very good question. So yeah, a single matrix element of the Laplacian tells you how likely are you to jump from state S to K, I don't know. And then, well, that would be just an operator here, which is just this is just the rank 1 matrix Sk. So sorry, like Ks, because so you are jumping to state K from S, and that's just a rank 1 matrix, and you multiply it with the transition weight. Well, more precisely, to get everything right, the square root. So if you have rate R from S to K jump, then that would be in this picture square root R times Ks rank 1 matrix. And if you have a classical Laplacian, then you translate it to this Lindblad, and then that's exactly the same picture, just much more complicated. There is no need for doing these super operators, but you get the equivalent description of the Markov chain, but now in a super operator language. All right. So, okay, now I want to describe how to simulate such Lindbladians, and there were already works on how to do that, but we have improvement over this, which I described where it stems from. Basically, we take the input model, which is described here, which is a sort of block encoding of the Lindbladian, which is a block encodes all the jump operators. So once again, I just describe here now the dissipative part of the Lindbladian, and that has this form. And sorry, this R, I don't know where it came from. That's a typo. Anyway, so you have, yeah, sorry, this symbol was an anti-commutator, and that just means that you take the sum of the two ordering of the product. So just if you don't know this symbol, and now this expanded here, so I expanded that thing, and this R just got here for somewhere. I need to remove it. So this is your Lindbladian, and I want to simulate it. And if you want to simulate it, you somehow need to have access to the description of your Lindbladian. And for that, it turns out that it's a very nice thing if you assume that your Lindbladian is given in a block encoding, which is some unitary matrix with the help of some ancillas. It encodes this sum of these operators, but you are labeling all the jumps with the corresponding labels. So it's sum over J tensor Lj. And so this is a matrix, and not necessarily a square matrix, but you can have a unitary matrix where the top left corner is just this particular matrix. And this is what we assume. And this is a more general input model than what previous work assumed. But it turns out that basically all the results that they proved can be converted into this picture. So they don't lose anything. We don't lose anything by assuming this input model. On the contrary, we gain a lot, and also we gain conceptual simplicity. It often happens with block encodings that somehow everything becomes much more universal and easy to describe. And okay, so
you're essentially representing the path with long-term qubits, right? Is that correct?
Yeah, that's right. Well, indeed, to represent these jump operators, you need log number of jump operators qubits. And in principle, you can always get away with dimension many jump operators if you have a succinct. So you can always represent Lindbaldian with bounded number of jumps. And then, so in principle, you can, even in the worst case, get away with doubling the system size. But then, of course, it depends on when you have efficient implementations of these particular Lindbaldians and so on. But one thing to note here, as the general restriction on block encodings is that whatever operator you block encode, that must have operator norm at most 1. And in principle, as long as an operator has operator norm at most 1, you can always find a block encoding. And in this picture, well, what is the and in this picture, it just means that, well, you can take this matrix and multiply it with adjoint. And if the matrix had norm at most 1, also it's multiplied by its adjoint has norm at most 1. And that is this condition that I described here. And if this condition is satisfied for the jump operators, so the norm of the sum of these dagger operator things are bounded by 1, then in principle you can have such a block encoding of your input. And please.
Yeah. This is maybe somehow related to the Feynman clock.
Sorry, what?
It's the concept of a Feynman clock. And I don't know if you just, maybe you connected this.
It's more related to, well, I will have a construction which is related to that, but it comes later on. It's more related to general dilation, purifications of quantum systems or unitary dilations of quantum channels. It's related to more that concept.
Yeah, I mean, if I remember correctly, the Feynman clock picture would also be a unitary map, right?
Yeah. Like this theme of representing some operators with larger unitaries, that's a very common thing in quantum information. That's called dilation in principle, this general idea. And yeah, this is also dilation like that.
Just one comment for non-classical light. As much as I love your condition, I really like it, it's not satisfied here, right? So you have to rescale. Or if you take the description of non-classical light with these LJs, this condition might be violated. Canonical generators they choose.
Well, you can always scale things.
Right, but the one they look at often.
So it's like in Hamiltonian simulation that you can either, like you can always scale up your Hamiltonian, but then it means that like unit time step becomes more hard to simulate. So there's always like you can push around normalization from time to Hamiltonian, just as like you can push around normalization from Lindbaldian to time in the evolution. That's equivalent. Yes?
So maybe that answers my question. So this is not the same as saying I have to have a contracted map.
Well, in some sense, it's contractive
Okay.
by this. Yeah, so this Lindbladian has a spectrum which is, the real part is less than or equal 0. So it's in some sense, maybe not contractive because it can preserve some things, but at least not expanding for sure. Yeah.
Just to understand the notation, this means you stack everything in a column.
Yeah, basically.
You can also stack them on the diagonal, like JJ, the same thing.
No, it's not the same thing. That's less efficient.
Oh, okay.
It's important that they are in the column.
Why?
Well, I will show you the simulation algorithm in the next slide. But you can, if you have this description, you can always put them in the diagonal.
Right.
But once you have the diagonal form, it might take a lot of time to put into this column form. That's yeah, conversion only goes in one direction efficiently. Yes.
that condition is not satisfied, you can still do the unitary dilation, just make it.
Yeah, you can just
Is that
shrink it and then basically divide it by some numbers until it's satisfied, and then do time, upscale your time. Yeah. All right. Yeah, and then prior methods, in contrast, depending on some of the norms. And in the case when you have an excessive number of jump operators, then it's really a huge difference if you need to take the sum of the norms versus the norm of the sums. You have a high-dimensional system, maybe you have highly non-overlapping Lindbladians, and then in principle you could have this efficiency that we achieve, but then if you use other methods, you would get much higher complexity. And this is not just a theoretical possibility. Actually, in our applications, this is the case. We really do gain from this representation a lot.
Can I ask you? So at the beginning you said that the original proposal required a huge bar. That's why the simulation is very expensive. But here, assuming that you have this block encoding, you're really kind of done the hard work of reduce the bar to very small size.
Yes, and one can imagine that in some cases it's hard to figure out these operators, but yeah, in some cases maybe it's not so important what are the details of your operators, and this is going to be next talk. We generally assume that for lots of systems, the intricate details of the operators are not so important, but as long as some guiding principles are satisfied, you more and less get the same type of behavior than what.
But of course, this does not simulate the path itself, right? It only simulates the interaction and the small system.
But you only care about the small system. The path is huge.
Right.
Okay, and now this is a way to simulate this Lindbladian using this block encoding. And so yeah, I just repeated the definition of what's block encoding of the Lindbladian. And it turns out that if you run this circuit, so what you do this unitary U, which kind of applies all the jump operators in superposition, because the first column of your matrix kind of contains the blocks of all the jumps. So basically, when you apply this U, and on your row, you apply all the jump operators in superposition. But, well, to make everything work out, it turns out that it's not good to be too greedy and do all the jumps with such a high magnitude. So what you effectively do here, when you apply the jump successfully, that's flagged by this 0B state, then you only accept this jump with some tiny probability. So this is a rotation with some small angle. It says, okay, if you applied some meaningful jump successfully, then only accept this jump with a tiny probability, and otherwise undo all the jumps. And then just measure everything. And it turns out that if you do this, then you are approximate. So square root d was this rotation angle here. It's a Pauli rotation. Then it turns out that this circuit approximately implements a delta time step of your Lindbladian. And the error turns out to be delta square. So this is a...
Oh, sorry. What is the operation in the middle? What's the gate?
Yeah, so this is controlled on the all zero state on these qubits. Do a Pauli rotation of this angle. Delta is a small thing. It's a small time step, and it turns out that you have to do a roughly square root delta angle rotation. And that kind of corresponds to a delta strong measurement in some sense, and also describes accordingly a delta time step of your Lindbladian evolution. And while it's approximately right, there will be an error which is order delta square. So as you shrink your delta, you will get more and more precisely to what you want. Of course, you will then repeat this process to make this delta roughly 1. And, well, it's like a trotter, first-order trotter simulation. Your individual errors shrink quadratically faster than how your actual time step shrinks. And then from this, you get this usual t square over epsilon scaling with. If you want to simulate your evolution for time t with epsilon precision, you need to take basically t square over epsilon time steps, and then it will be epsilon precise. And so this now focuses on the dissipative part, but you could simulate the coherent part as well if after doing this, you also apply a delta time step Hamiltonian evolution with this coherent part. And then repeat this circuit over and over, and then you apply the joint Lindbladian. So it can be applied also for coherent part. Yes?
So I assume it's conditional of measurement turned into O0 or O1, is it?
What's conditional, sorry?
When you do the measurement, your state will only be true when the outcome is O0 or
No.
no. Why do you want to measure them?
Okay, so then, yeah, you're right. Basically, measurement is you don't even need to measure them. Just forget about them. This is like the bath. Okay, so now you are interacting with your bath, and then you forget the interaction and replace them with new, fresh 0 qubits. So now this is basically how the bath is modeled by interacting only with a few qubits at a time, and then you refresh the bath, meaning that you replace the qubits by new zeros. You can measure them, throw them away, do whatever you wish. And now this shows you how, well, it's basically a very efficient simulation of the bath. And also it sheds light on how rapidly your bath needs to be refreshed in order this master equation to be the right description. So it is not only an algorithm, but it also gives you a proof of how quickly your system needs to be refreshed to have your Lindblad evolution, good description of your system.
How do you actually refresh this measurement?
Well, usually you assume in quantum computing that you can measure things, you can initialize qubits in 0 states. That's just one functionality that we generally assume from quantum circuits. Yes?
So we said we can just ignore the measurement results, but if we were to look at them, is there an intuitive understanding of what the measurement results, if they coincide with either having the decay part or the jump part of the Lindbladian?
Yeah, so basically, they kind of, yeah, if you do it rapidly, then eventually you will get some label out, and then basically say, oh, actually now a jump J happened. Oh, now a jump K happened. And you kind of get this information out of it. But that's okay. I mean, this is a incoherent process, so you inevitably learn something about your system. That's fine. You can remember it, but you don't have to.
I think the question is whether you can just by reading whether it's 0 or 1, you can tell whether a jump has happened then?
Yeah. Yes. But even if a jump didn't happen, you still did something to your system.
Right, which is the decay.
Yes. Yes.
Because all the qubits are entangled with the lower register, right? So your measurement will, if it's a different outcome, the final product will be quite different.
Yes, but it's it's similar to how you just do classical Markov chains. You know which transition happened in every step, but your distribution, in a probabilistic sense, evolves as the true distribution you want to simulate.
Yeah,
of course, you observe trajectories of the Markov chain, but overall, the good description is still the distribution that you care about.
That's what I'm asking. It looks like if one particular outcome of the measurement will provide a particular trajectory of your target.
Yeah, sometimes it's called a trajectory picture simulation.
Okay. All right.
Yes.
Okay.
We had some question. Yeah, there in the please.
Yeah, it seems like we're in the peppering phase, so it's okay to keep asking questions. So is the coherent part so cheap that like doing it after is not much difference in cost as to like combining it into the block encodings?
It depends on your, how difficult is to describe your Lindbladian, your Hamiltonian, but I'm just saying that this is a Trotter-style simulation thing, and you can do Trotter-style for the distributive part, and also just interlace with Trotter-style Hamiltonian simulation, and then they all together give rise to the ultimate Lindbladian, which involves both coherent and incoherent evolution, and they will just, the same thing happens that you still approximate your time evolution with to delta time step with delta square precision. So the two errors don't interfere badly with each other. Yes.
So just want to make sure, so this, as a advantage of this is automatically CPTP, this approximation.
Yeah, this is a CPTP approximation, which is important, just like the object that you want to. And then it's a difficult thing to achieve. And exactly for this strong requirement, I don't really know how to get an analogy of higher order trotter steps, because I don't know how to make those the CPTP. But we have a question there.
Maybe it's obvious. How are A and B related to M? What are A and B? How many qubits do you need?
This is just how your block encoding. This is arbitrary. Just.
If you try to calculate the cross operators for this e to the d delta L hat, which of course have to exist, right? There is a first order approximation of those, and I think they don't give the u, but they give the same square root of delta approximation. So this can be viewed as an approximation of the cross operators for that particular positive map up to a delta squared error. I think there's an analogy there which you could write down.
Yeah, that makes sense. Okay, so, well, I won't have time to go into these details, but here is a proof of why it works, and the key takeaway here is that you get some delta square here, and this delta square means that you are doing the Zeno effect. So delta square is the Zeno effect, and delta is the times that you evolve, and you can read it on paper. I don't have time for this. But what is more interesting is to tell you this compression trick. So this was a trotter-like simulation, and therefore your scaling with time was quadratic, and your precision scaling was 1 over epsilon, which is not log 1 over epsilon that you generally want. And there is a nice trick to do this, and that is, okay, so now this is just the circuit of doing all these weak measurements on new ancilla qubits all the time. I didn't do anything, just basically explicitly described all the different ancillas that do. So this C prime is the circuit for doing the weak measurement. And then this is just doing it. And while there is some slight tweak that you can do it, and basically you move this weak measurement weakness into some qubit state. That's the Y states. And somehow this is just moving this weakness of the measurement out of the circuit. This is just a small trick. And then basically all these things just simulates your weak measurements on these new fresh copies of the ancillas every time. But then a slight issue with this that because I move this weakness of the measurement to quantum state, then I will have some tiny failure probability. So now I need to post-select on the outcomes. In the previous picture, didn't have to do any post-selection. In this picture, I need to do a slight post-selection. But the advantage of this, that the weakness of the measurement that is now encoded in a quantum state, and this circuit does not contain any information about weakness and so on. And now the good thing about this is that you want to now simulate, say, your time evolution from time equals 1, constant time. Then you do this, several repeated small time steps. But because your overall time is 1, you are expected to have only about a single jump throughout all the process. You are not expected to see more than a few jumps. And therefore, you can actually say that this initial circuit that describes all the weakness of the measurements, that will be a state of low Hamming weight. And now, what happens here is that it's a very wasteful picture because you have an extremely low Hamming weight state, and then you are acting mostly just trivially on it, and then you have a huge waste in resources and everything. It turns out that you can just simulate somehow the action of this structured circuit on the low Hamming weight part of this initial state and end state using some compression techniques, and that way, you will ultimately only have a logarithmic dependence on the number of slices that you take in your time evolution, and therefore doing this compression actually will implement time evolution from time 1 with logarithmic dependence on resources for slices, and therefore ultimately logarithmic dependence on the precision.
One small question is that is average. That's that L value.
So yeah, this is some y rotation of delta angle. Oh, yeah, that should not be there. I don't know how it will go there. Sorry for that.
Yeah, the question is, since you're going to measure this bar reset anyway, why can't you reuse this qubits?
Well, you can't reuse them because sometimes they will say, okay, a jump happened, and the jump label will be there. So it will be, in particular, not the 0 state.
Then you just reset back to 0.
Yeah.
What's wrong with that?
But that requires some classical control and conditional things.
Right, you measure and control. And
Yeah. Okay, yeah. So
that's fine.
yeah. So if oh, sorry, yeah. So if you are doing this circuit, then yeah, just reset all the time. Right. But now I'm describing a way, but this has complexity which is t squared over epsilon.
Oh, gotcha.
And
so you want to do some compression gadget.
Yes. So now it will only use some. Ultimately, I will compress all this. So imagine, this is like the thing that we wanted to do, but it's entirely resource wasting. But all these many ancillas and everything can be compressed to only a few ancillas using the realization that this initial state has low Hamming weight. And so this low Hamming weight initial state, having this excessive number of ancillas is effectively compressed to only a logarithmic number of 1. And, well, you analyze it and it works.
So just a notation question, C prime is the U that you have on the previous slide?
It's not exactly that. It's something which doesn't include this weakness parameter. So this rotation is outsourced to a quantum state. Okay, this square root delta rotation is now outsourced to a quantum state, but something circuit which is almost like this. Okay?
So this only matters when you completing this condition is strictly less than 1. So if is a, I mean, you have a sum here, J dagger L is exactly provided.
Yeah, okay, but that's a very special case. Yes.
Okay. Yeah, so in that case, you don't need to worry about this, but that's not.
Yeah, I think that you can improve this, but in general, and so yeah, this compression technique was used by Cleve and Wang in their Lindblad simulation algorithm, and they showed first how to make Lindblad simulation, which is roughly linear in time and logarithmic in precision, and we get the same thing, but on top of their results, we still preserve this improvement from depending on the norm of the sum rather than the sum of the norms. So we preserve this advantage, combine them to get best of both worlds, best dependence on the norm of the jump operators, and best time dependence altogether. So this is our simulation algorithm. And okay, so now what kind of Lindbladian do we want to simulate? And well, we want to simulate thermalization, and there is something which is called the Davis generator, which I don't have to now time to explain in detail, but this is something where you probably have the fixed point where this map converges to is the Gibbs state exactly. And this is a standard way of doing it, but it has problems. This is called the Davis generator, and we want to simulate something like this, but it's folklore knowledge that this Davis generator, although has these analytic properties why we like it, but it has some unphysical exponential relaxation time because it has operators corresponding to every energy difference in the spectrum of the Hamiltonian. So now we want to prepare Gibbs states, and so we care about Hamiltonian of the system. And these can be exponentially close to each other, and in principle, Davis generator can distinguish exponentially small differences in energies, which is unphysical. There is this time energy uncertainty principle that if you evolve your system for a certain time, you can't resolve energies more than roughly 1 over time precision. It's Heisenberg-like scaling in precision. And so this is a very nice analytic description of something which is unphysical, unfortunately. So now I have to ask the question, is simulating nature equal the same as preparing Gibbs states? Well, simulating nature on a quantum computer should be easy. As I described you, we have good ideas how to do it. In principle, a quantum computer should be able to simulate quantum mechanical systems. On the other hand, it's known that preparing Gibbs states can be QMA hard in the worst case. So what's going on? Something is not right. So well, although in typical physical systems, Gibbs states can be indeed prepared, but not in that there are systems where it just doesn't thermalize quickly, and so nature will get stuck in some local minima and will not converge to the Gibbs state, which is QMA hard, but will converge to some state which it likes to converge to. And that simulated nature means getting there where nature gets, not getting there where mathematical physicists think we should get. Okay, it's of course they know this is the case, but we just we have an ideal object, and nature doesn't always get to the ideal object, but it gets to where it gets, and we only need to simulate where it gets because we want to understand nature, not where it should get. Well, at least from physical point of view. And then there is a very nice paper which is out for about 5 days now or 6 about a local minima in quantum systems, and Anthony is one of the authors. And the idea is that they show that indeed quantum computers are good at finding local minima in your energy landscape, and that is something where actually classical computers can't do it efficiently. That seems to be the most likely outcome. So getting to local minima is what you care about, and you can do it in a quantum computer as you expect, but it seems that classical computers struggle getting to even local minima, let alone global minima, which also quantum computers can struggle with sometimes.
Can you dig into why classical computers even have to get to local minima because set of points?
I think they actually have some Hamiltonian where global minima is the only local minima is a global minima, and still classically hard to get to.
I basically embed a construction into the Hamiltonian so that it's universal. So that the hardness comes from UPP functions.
Okay, and so we want to simulate thermalization in nature, but the Davis generator, although has nice analytical properties, is unphysical. And so we should go back to first principles, and there is a very nice paper about coarse graining the master equation, which derives an alternative Lindbladian, and this is what it is. I'm sorry for this, but this is what they derive, and it is from first principles. And okay, the basic takeaway message that if you would have this integral over these omegas and everything, if this time would be infinity, you would get back the Davis generator, which is unphysical, but this time is finite in the description. And so you only need to simulate this ugly thing. But this, at least, now is no longer unphysical. And we have tools to do this. And so whatever you see here, this is something that we call, this is often called operator Fourier transform. And this is somehow Fourier transforming the jump operators with flat weights in this case. And these are the jump operators of your Lindbladian, which is now in a continuous case. You don't have a sum of jump operators, but you have a continuous sum of jump operators, which is the integral. Now you can discretize it, and you can discretize this integral to a sum, and then you can do this operator Fourier transform in a discretized picture, and that's a quantum operator Fourier transform. And okay, I really don't have time to explain the details here, but the key thing is that we show that discretization suffices at a not too fine-grained level, so you have only logarithmic number of qubits, and this operator Fourier transform can be done with quantum Fourier transform very efficiently. And so all the costs that appear here is logarithmic in t and all these parameters. And there was a question there.
This is a good question. Is the integral in your previous slide at the bottom still a Markovian process, or is it a Markovian or not anymore?
Yeah, this is a Lindbladian. Sorry, yes, it's a Lindbladian, so it's still CPTP and everything. It is just continuous sum that still has the same properties. In principle, you can rewrite it using different operators to a finite sum, but that may be difficult to know what are these operators. But this is a way to describe the operators in a smooth way. Now it's an integral, but at least we can approximate it with discretization.
Sorry, what's the small a here again?
Pardon?
What's the small a here again? The notation?
Yeah. Sorry. Yeah, that previously it was J. So this is the labeling of the jump operators.
And what's happening?
that's a set of jump operators. So, yeah, okay, this is, okay. In this picture, you have some initial jump operators that get modified by the interaction with the system. So it's like a kind of, you get to the jump operators in your ultimate Lindbladian at the two-step process. You have some initial jump operators which get scrambled by this interaction, and that's how you get to the ultimate jump operators that you need to eventually simulate on your quantum computer. Yeah, and in often case, you can probably get a good simulation by just having these as something like local Pauli jumps or something like that. Think about these all local Paulis as the set of jump operators AA or something like that, and they get scrambled by this interaction, and the Fourier transform, operator Fourier transform is what you need to ultimately simulate.
What's claimed is that for any arbitrary choice of the jump operators, is the thermalizing
No, well, actually, this is something that they couldn't derive, but we did show that if this system is mixing rapidly, so it thermalizes in a reasonable time, then actually the fixed point will be almost the Gibbs state. So if rapid thermalization implies that this approximate Davis generator actually has an approximate Gibbs fixed point. And this is something that they couldn't establish before, but with our techniques, we have this analytical result on top of efficient simulation.
So the choice of A comes into this assumption of rapid mixing. So like
yeah, like your mixing time can depend on the jump operators, indeed, and the Hamiltonian and lots of details. Let me quickly get to the last slide because I'm getting out of time. Anyway, so there is this physically motivated system which is supposed to describe a thermalization in nature, and now we can simulate it. And with our Lindblad techniques, you can simulate the evolution, time evolution t with linear resources in time t, like in Hamiltonian simulation, and logarithmic in all other parameters. So it's time t times log of other parameters, and then the complexity of encoding your initial jump operator. So it's very nice. We don't expect that you can get much improvement over this. And now you can simulate thermalization in nature. And well, we also have a version where we move this incoherent process to a coherent Szegedy-type quantum walk. And there we can not only prepare the Gibbs state or the approximate Gibbs state, but a purification of the Gibbs state, and maybe get even some speed up in the process. And so this is just telling you that once we have this very nice analytical framework, we can also make it more coherent and get additional quantum tricks like quantum walks to get even more improvements in the outcome and the process and the complexity. And so, yeah, I have these open questions because I'm really running out of time. I just want to say them. Yeah, so very good question is now, in which physical systems can we expect rapid convergence to the Gibbs state, or how we can bound this gap and mixing time of these processes. And because we are ultimately simulating some noisy process, maybe our algorithm can be made a bit more noise resilient. We don't need full error correction for everything, maybe we do. It's a very interesting question. And then, well, the last question is kind of a joke, but we hope that you can actually do something useful with simulating this. Maybe you can finally get to ground states of molecules quicker because, I mean, supposedly nature gets to the ground state of molecules by just doing some interaction and driving it there. And all sorts of applications are hopefully emerging from this. That's our hope. Thank you.